Hello everyone, this is lecture 10 and 11, Infectious Disease Modeling. So in these two lectures, I want to talk about various discrete epidemic models using system of different equations. The mathematical analysis and modeling is an important part of infectious disease epidemiology, and applications of mathematical models to disease surveillance data can be used to address both scientific hypotheses and disease control policy questions. And modern infectious disease epidemiology relies heavily on mathematical modeling to characterize the complex interaction between the biology and environment of human or animal host. That's kind of the motivation for this type of lecture about infectious disease modeling, and we're going to approach this infectious disease through the lens of mathematical models and specifically system of different equations. Before we dive into a specific model, I want to give you some definitions, some example related to infectious disease. So definitions about epidemic, which is a widespread occurrence of infectious disease in the community at a particular time. And there are some differences between epidemic and pandemic. So for epidemic, that is an event in which the disease is actively spreading, whereas pandemic relates to geographic spread. In addition, epidemic often used to describe a problem that has growth out of control. On the other hand, pandemic describes disease that affects a whole country or the entire world. One of the example that we can always relate back to this particular topic is COVID-19, which is a very recent outbreak at some point actively spreading throughout the world, and it's not only affects one country, it's actually affecting the entire world back in 2020 to 2021. Some of the more famous epidemics and pandemics that happened in the past, one of which is the Black Plague, killed more than 75 million people from 1347 to 1351, including those who died in Europe, Middle Eastern lands, China, and India. In 1918, you have Spanish flu pandemic killed well over 50 million people in 1 year, including 675,000 Americans. The smallpox pandemic in the 20th century claimed between 300 and 500 million lives, and in 1980, smallpox was declared eradicated due to the massive campaign launched by the WHO, the World Health Organization, in 1959. It is the only human disease that has been eradicated. Tuberculosis pandemic continues to kill over 1.5 million people annually. Despite the availability of effective treatment, the bacteria that causes tuberculosis is increasingly resistant to drugs used to treat it. The HIV pandemic has killed over 39 million people since 1982. However, with the availability of effective HIV treatment, it is no longer considered a pandemic. It is an epidemic or hyper-endemic in specific regions. The swine flu pandemic was an outbreak of H1N1 influenza in the United States in 2009. Over 60 million Americans were infected, resulting in 270,304 hospitalizations and more than 12,000 deaths. The incidence of dengue fever has grown dramatically around the world, with cases reported to WHO increasing from more than 500,000 cases in 2000 to 5.2 million in 2019. The largest number of dengue cases reported was in 2023. The WHO region of the Americas reported 4.5 million cases with 2,300 deaths. A high number of cases were reported in Asia, specifically in Bangladesh of 321,000 cases, Malaysia of more than 100,000 cases, Thailand of 150,000 cases, and Vietnam with 369,000 cases. And of course, COVID-19 pandemic caused by the SARS-CoV-2 virus claimed nearly 7 million lives worldwide between December of 2019 and May 2023. The WHO declared COVID-19 a pandemic on March 11 of 2020, prompting shutdown across the globe. And this is the graph of COVID-19 cases that show the number of new confirmed COVID-19 cases between February of 2020 to April of 2020. Some of which are hospitalized, some of the cases are hospitalized, some of the cases not hospitalized, but overall this is the cases of confirmed COVID-19. Now, the questions for modeling the epidemic is that what is the risk of an epidemic to occur, and how severe is the epidemic? The natural question is what proportion of the population will become infected, and unfortunately, the question we have to ask is what proportion of the population will die from the disease. how long the epidemic or infectious disease is going to last. Right? So it's obviously going to be different from one disease to the other. Are all individuals at risk of becoming infected? And how far will it spread? So this one depends on effective interventions such as COVID-19 cases. For COVID-19 back in 2020, that it spread very dramatically and very quickly, and therefore we have to implement interventions such as isolations, wearing masks, and later on vaccinations. And doing isolations prevent people from traveling from one place to another place and therefore minimize the spread of the virus over time. And what impact does a particular intervention have on the risk, severity, and durations of the epidemic? So again, for COVID-19 cases, because of the interventions of isolations, wearing masks, you reduce the number of cases infected by the virus and also minimize the transmissions of the disease from one person to another person. So in mathematics, usually we use compartmental models to model infectious disease transmissions. Most often, we use a system of different equations or discrete time model. For continuous time model, we use differential equation. And we can always increase the complexity of the model of each model of considerations by thinking about if you want to model with demographic or without demographics. We also can consider if one person get infected from the disease, get recover, and somehow lost the immunity of the disease. That's also add into the complexity of the model, and also the inclusions of the chronic carriers. Some can carry the virus but without obvious symptoms. Some people get incubation period, latent period, without showing any symptom until much later. For example, the COVID-19, again, the incubation period can go up to 14 days, up to 2 weeks, and during that time, people can carry the virus but without showing any symptom whatsoever, and they don't get fully infected until 2 weeks later. So I want to take this opportunity to go through a little bit of details of the dynamics of the SIR model, the interaction between the susceptible individuals, infected individual, and how people can recover from a disease. So let's just make the assumptions here that consider a disease that is spreading throughout the United States, such as a new flu. The CDC is interested in knowing and experimenting with a model for this new disease before it actually becomes a real epidemic. Consider the population divided into 3 different categories: susceptible, infected, and remove or recover. We make the following assumptions for our model: that no one enters or leaves the community and there is no contact outside the community. So we have a closed system in this particular context. So if each person is susceptible, which is able to catch this new flu, infected eye currently has the flu and can spread the flu to other people in the susceptible compartment, or remove or recover from the disease. Right? So this person already had the flu and will not get it again, which includes death. Initially, every person is either S or I. Once someone gets the flu this year, they cannot get the flu again. So you have a permanent immunity. The time period for the model is per week. Now I'm going to write out some terminologies in order for us to use it a little bit later in the model. So you have S of n, or you can use S sub n, is the number of individuals in the population susceptible to the disease. I of n, or I sub n, is the number infected after period n. And R of n, or R sub n, is the number of individuals recover or remove after period n. Now we have the following flowchart. This is again the compartmental model, including 3 different compartments: S, I, and R. S, I, R. Again, S is susceptible, I is infected, R is recover or remove. Now, an individual that is susceptible to the disease come in contact with the infected persons, and the populations going from susceptible populations to infected population at the rate of alpha. And people in the infected compartment can recover or remove from the infected populations at the rate of beta. And we're going to use this flowchart or schematic to build up our system of different equations, our model. And susceptible individuals become infected when coming into contact with infected populations. And there is only one term in the difference equation, and that is the term represent the reductions in the populations. That is S sub n plus 1 minus S sub n equal to negative alpha times S sub n times I sub n, for alpha is the infection rate or transmission rate or the rate at which the disease is spreading. And we assume that alpha to be a positive number. And that's it for the susceptible compartment. Now we're going to move on to infected compartment. There are a few things that we need to consider in the case of infected compartment. So the infected populations is increasing by the number of susceptible people that come in contact with infected people. And the infected population is decreased by the number of people recover or remove from the disease. So there are two terms in the different equations of the infected compartment. The increasing term, that is, you receive the people from the susceptible compartment. That shows the reductions in the population because people are recover or removed from the disease. So the first point is that the infected populations is increased and it is decreased. And the difference equations of the infected compartment is I sub n plus 1 minus I sub n, and this is equal to alpha times S sub n times I sub n minus beta times I sub n. For beta in this case is the recovery rate and is actually equal to the inverse of the average durations of infectiousness. So for beta is the recovery rate, and is equal to 1 over average durations of infectiousness. Now we're going to move on to the last compartment, is the recover compartment or remove compartment. So the recover populations is increased by the number of infected individuals recover from the disease. So the recover or remove compartment or populations. So the difference equations of the recover compartment is R sub n plus 1 minus R sub n equal to beta times I sub n. And we need to include one condition for the populations is n equal to S plus I plus R. So for the SIR model, the system of different equations include three equations. So the system is S sub n plus 1 minus S sub n equal to negative alpha times S sub n times I sub n. The second equation is I sub n plus 1 minus I sub n equal to alpha times S sub n times I sub n minus beta times I sub n. And the last equation is R sub n plus 1 minus R sub n equal to beta times I sub n. So I'm going to name this is equation 1, this is equation 2, and this is equation 3. And the next thing that we're going to do is we're going to find the equilibrium point of the system. That is, to find the equilibrium point, we're going to let S sub n plus 1 equal to S sub n equal to S, I sub n plus 1 equal to I sub n equal to I, and R sub n plus 1 equal to R sub n equal to R. Unlike other population dynamic models such as prey and predator model, competitive model, or cooperation model, the SIR model in the infectious disease model, the I compartment play a much more important role compared to the susceptible compartment and the recovery compartment, and you will see in a minute why that is the case. So we have three equations in the system. So from the first equation, you have that the left hand side is S minus S equal to negative S times I. So that is negative S times I equal to 0. You have two scenarios. You need to consider two scenarios in this case. That is either S equal to 0 or I is equal to 0. For the case of S equal to 0, there's no susceptibles, and that is not really realistic in the case of infectious disease model because you need people to be susceptible to the disease, otherwise we don't have any system to analyze. So this is not realistic for the case of S equal to 0. So here's no susceptible. And for the case of I equal to 0, this is called the disease-free equilibrium. So at this point, nobody gets infected by the disease at all. So that from the first equation, if you do a similar analysis for the third equation, you will see that I is also equal to 0. So from the third equation, you have beta I equal to 0, or I is equal to 0 in this case. And from the second equation, which is a more important equation for us, you have alpha times S times I minus beta times I equal to 0, and I is a common factor here. You're left with alpha times S minus beta equal to 0. In one scenario, you have I equal to 0. In the other scenario, you have alpha times S minus beta equal to 0, or S is equal to beta over alpha. Now, the equilibrium point that we have is SIR equal to beta over alpha, comma 0, comma 0. So equilibrium point is SIR equal to beta over alpha, comma 0, comma 0. So that is the analysis of the SIR model, or the system of different equations. In this case, you have three equations. One equation is for the S compartment, susceptible compartment. One equation is for infected compartment. And one equation is for the recover or remove compartment. And we found that there is one equilibrium point, that is S equal to beta over alpha, R equal to 0, and R is equal to 0. Now we're going to look into the solutions curve of this model with some given parameters and initial conditions. So in this case, initially, we're going to have that S of 0, or S sub 0 is equal to 995. So there are 995 people that are susceptible to the disease. I of 0 is equal to I sub 0, or equal to 5. So there are 5 people originally infected by the disease, and there's no recovery at this point of considerations. So the total number of the populations in this community is 1,000. Again, this is a closed system, right? We don't want anyone to enter or leave the community. So N is equal to 1,000. And for the parameters, alpha is given to be 0.001407, and beta is equal to 0.6. Again, beta is the recovery rate, which is 1 over the average durations of infectiousness. And of course, the value of beta will change from one disease to another disease, as well as alpha. But assume that you have a flu and you contract with the flu, and the average duration of the infectiousness is about a little bit more than 1 week. So the recovery rate is about 60%. Now we're going to use this number and input that into Excel to observe the solution curves. So I'm going to use Excel at this point. So we're going to use Excel to generate the solution curves of the system of different equations for the SIR model. So I'm going to create 4 different columns. The first column is for time period N. The second column is for susceptible. The third column is for I, infected compartment. And the last column is recovery or remove compartment. Initially, we're going to see 995 people in the susceptible compartment. 5 people get infected from the disease, and there's no recovery at this point of consideration. There are 2 parameters that we need to consider for the model. The first one is alpha equal to 0.001407, and beta is equal to 0.6. Now I want to see the population evolutions for up to 20 time periods, so I'm going to create 20 rows starting from 1. So I'm going to do equal sequence. We want to generate 20 rows, just 1 column starting at 1, and we're going to take 1 step at a time. So it's automatically generate 20 rows for you. For S sub 1, we're going to use the different equations formula for S. So we get this is equal to S0, which is 995, minus alpha times S0 times I0. And then you need to make sure that the parameters stay put throughout all the calculations. So for I1, you have the equation for the I compartment to be I0 plus alpha times S0 times I0 minus beta times I0. And for R1, you do R0 plus beta times I0. And again, make sure that all the parameters stay put throughout the calculations. Now we're going to update the formula for the other rows as well. And this is what you're going to see. Now to observe the solution curves, we're going to wrap this row. Use Shift and Control downward button to select all the values in these 4 columns. Go to Insert, go to this scatter plot, and scatter plot with lines and markers. And this is what you're going to see. This is the solution curve. And we're going to change the title and the legends of this graph a little bit. So click on the graph, go to Quick Layouts, and change that to layout number 1. So here, let me expand this out a bit. So I'm going to change the title to SIR model. The x-axis title is going to be time. The y-axis title is population. The legend here, so you have a different solution curves. The blue one is for susceptible, the orange one is for the infected, and the green one is for recovery or removed compartment. So I'm going to change the legends there. You select the legends, go to select data. You have 3 series here. Series 1 you change to susceptible. Second series you change that to infected, and the last series you change that to recover. And that is what you see for the solutions curve for the SIR model. Now let me switch back to the note. Again, this is the classic standard SIR model. For S is susceptible, I is infected, and R is recover or remove. The total number of people in the community of consideration has to be equal to S plus I plus R. There's no birth or natural death from this dynamic. So in this case, we say that without any demographic. And the transmission rate is alpha, and the recovery rate is beta. And this is the SIR model that we see earlier. Here again, alpha is the transmission coefficient or transmission rate, beta is the recovery rate, and beta is equal to 1 over the average durations of infectiousness. We found the equilibrium values, just one equilibrium point at this for this particular model, that is S equal to beta over alpha, I is equal to 0, and R is equal to 0. And using Excel, we can actually produce this solution curves with the initial value of S to be 995, initial value of I is equal to 5, and initial value of R is equal to 0, with alpha is equal to 0.001407, and beta is equal to 0.6. So the solution curve here give us, this is S sub n, this is I sub n, and this is R sub n. So the original, so initially you have 995 people susceptible to the disease. At some point, the number of susceptible decreases because the number of infected cases increases over time. And simultaneously, people will recover from the disease. And at some point, the disease will eventually die down, and everyone become either fully recover or removed from the system. And the question is, will there be an epidemic? So epidemic will occur if the proportion of infectives increases with times. So that is I sub n plus 1 minus I sub n greater than 0. So you want this difference equations to be positive. Or alpha times S sub n times I sub n minus beta times I sub n equal to I sub n times alpha times S sub n minus beta to be a positive number. So when you want this to be a positive number, I sub n has to be a positive number, right? Because you don't want I to be 0, which is a disease-free equilibrium. We want to know if the epidemic occur or not. Therefore, you have to exclude the value I sub n equal to 0. And I sub n can be a negative number. So therefore, in this analysis, we want I sub n to be a positive number. This product is positive number and I is positive, therefore this expression has to be a positive number as well. Implies that alpha times S sub n minus beta greater than 0, or S sub n is greater than beta over alpha. Thus, the infections will only invade if the initial proportion of susceptibles, S sub 0, is greater than beta over alpha. So if S sub 0 is greater than beta over alpha, then the epidemic is growing. And if S is less than beta over alpha, then the epidemic is shrinking. In addition to this number of S0 greater than beta over alpha, there's another way to analyze this particular model in terms of something called the pre-production number. Let R0 equal to alpha times S0 divided by beta. What I did is that I multiplied both sides of this inequality for alpha over beta, and therefore the infection will only invade in the case of R sub 0 greater than 1. And this R sub 0 is called a pre-production number. R0 is a key epidemiological measure for how infectious a disease is. The definition of this is that pre-production number is the average number of people an infectious person will infect, assuming that the rest of the population is susceptible. So when R0 equal to 1, this is going to be a threshold between epidemic and no epidemic. When R0 is greater than 1, the disease can invade. And when R0 is less than 1, the disease will die down. And I have this following picture represents the different R0 for different disease. For Ebola, you have R0 to be 2, that is, you have one person infected from the disease can subsequently infect 2 other people. The COVID-19 R0 is around 3. HIV R0 is 4, for mumps R0 is 10, and for measles R0 is 18. And the reproduction number for the standard SIR model, the infections will only invade if R0 is equal to alpha over beta times S0 greater than 1. Now, for an average infected individual, we can actually calculate the number of people that that individual can infect over the lifetime of the infections. So an average infected individual is infectious for a period of 1 over beta days. And the individual can infect alpha times S0 individuals per day. And therefore will generate alpha over S0 divided by beta new infections over its lifetime. So this R0 of alpha times S0 divided by beta tell you the number of secondary infections from one sick person. So there are other epidemic models that you can encounter in mathematical epidemiology. You can have SI model when everyone is susceptible to certain disease, and when you contract with the disease, you stay in the infected compartment forever. One of the disease that you can consider is the HIV model. Even though at this point you have effective treatment for HIV patients, but there's a lot of regions around the world that cannot get access to that type of effective treatment. So it always makes sense to consider the SI model for HIV disease. So for SIS model, this is called the disease without immunity. People are susceptible to the disease. When people become infected, they stay in the infected compartment, but eventually they are free from the disease but automatically go back to the susceptible compartment. And the disease that have this type of models is sexual transmission diseases. So this is disease without immunity. And STDs. So for SIRS model, this is the finite time immunity. So the people in the susceptible compartment are susceptible to the disease. When become infected, they move to infected compartment. Eventually, they recover from the disease and stay in the recovered compartment for a short period of time before going back to the susceptible compartment. And usually, that is the common call that we can consider for this model. So this is the finite time immunity. You can have SEIR model. In this case, you have a new compartment. It's called the E compartment or the expo compartment. There are certain diseases that the patients will contract the virus, but stay in the incubations period or latent period. They show no symptoms whatsoever for a short period of time before they become fully infected from the disease. One of which can be the disease that we can use for this type of model is for COVID-19 or dengue fever. So in this case, E, the expo compartment. You have incubations period. So in no symptoms. And some of the disease that we can consider are COVID-19 or dengue fever. Again, these are just a very basic model. You can increase the complexity of the model by adding more terms and consider a more realistic scenario. You can start with the basic standard model, the SIR model, and you can consider that the system is not going to be a closed system. That is, there's the birth rate and there is the natural death rate imposed into the system. So this type of model is the model with demography. And you consider we're going to make the assumptions that the birth rate and the death rate is going to be the same, and we're going to use the letter mu for that. So the birth rate is mu, the death rate is also mu. In this case, the death rate is the natural death rate. When a susceptible person come in contact with the infected person, disease can transmit at the rate of alpha. When the person get infected, and then the infected person can recover from the disease with the rate of beta. Okay, so this is the model that we're going to do next in our lecture. That is a SIR model with a demography scenario.